that's what I have a degree in. And so I was thinking, like, what's an interesting topic in astronomy to talk about, and I couldn't decide until this morning. I was like, oh, I could talk about this or about that or about something else. But I decided, since these were in the news recently, that I would mention that and, like, you know, have Christine's judgment because she is PhD. Anyway, so recently there was a discovery with gravitational waves, which some of you may have heard of, that it's important and stuff. So this is going to be a very brief intro to them because they're actually really complicated, and coming up with a simple way of explaining them.
Yes.
No.
It's too complicated for us.
No, it's not. But like having 5 minutes to explain complex physics ideas was like a challenge.
Well, I'll be 4.5 minutes more than we know.
Okay. So this is just a picture of like waves, like So when you drop like a rock in a pond, it makes ripples. And they just kind of look something like that. So this happens, light is the same sort of thing. When you talk, it's the same thing because you're making vibrations in the air and then your ears pick that up. So waves are how we detect a lot of things, or how we see because of light waves, and they're also how we hear and things like that. So in this context, so gravitational waves are like that, only on a much bigger and more complicated scale. So, for one, they're ripples in what we call space-time, which the simplest way of putting it is that we have 3 dimensions, like side to side, up and down, if you've played video games, and then like back and forth. So kind of like 3 different dimensions, and there's time, which counts as like the 4th one. In physics, we consider them all to be like one sort of, I don't know, like the way I always describe it when I'm trying to explain this is like, if say you have like a giant rubber sheet, and when you drop something on that, like say a bowling ball, it's going to dip down a little bit. So that's what this picture's showing. You just have like a sheet of the grids just help accentuate the point. But when you put a massive object in like a plane of space-time, you're actually bending it. And so, for example, this could be the sun. So it actually makes a dip in basically in the rubber sheet that is our universe, if you want to think of it that way. Yeah. So if you have like your rubber sheet, which if I had one I would show you, but you put like the bowling ball in it and it makes a dip a little bit. So imagine it like that, because it's easier to picture than trying to get your head around like 4 dimensions. Okay, so well, it just did something weird. Okay. Oh,
I think you moved the cable.
There we go. Cable came out a little bit. Here we go. Maybe.
Try to just exit, escape PowerPoint and open it up again, because we just...
Okay. There it is again. Alright. Okay. Always technical.
Someone should have jumped up and done a PQA commercial during that brief outage. I'm taping.
I was hoping for a song from
Okay.
We could have had a song, that's right.
So anything that has mass or is heavy will create like a dent in this rubber sheet. So anything that like the sun, Earth, so the more massive the object, the bigger the dent. Like if you're on a trampoline, like a heavier person's gonna make it bounce more.
I make a bigger bounce.
Yeah, than a smaller person. So Mike would make a bigger like bounce than Paula. You know, so like that's the idea of like the more massive it is, the bigger of an indent you get. So in order to detect these, which I'll explain that a little bit later, the heaviest objects or the most dense objects we can use to measure things are black holes. So a very brief description of what those are, because those are not easy either. So this picture looks a little more complicated than it is, but there we go. So this is basically how what a black hole is leftover from a giant star that exploded. So a star like the sun, when it dies, it's gonna go kind of like, if you see at the top where it says sun-like star, it's gonna become a bigger star and eat us, and then eventually its gas is just gonna fade away into space. And leave behind just its core, and then it will leave gas, which will eventually make other stars. But anyway, a bigger star that's say like 8 to 7, well, what is it, 8 to 10 times the mass of the sun, that grows into be an already pretty huge star, which then becomes even bigger when it starts to die. But when it dies, it explodes in a supernova, which is, you may not have heard that term, but it's an exploding star. And there's a couple options that can happen when you do that, and one is a black hole. So basically, it's just it collapses in on itself to the point where it's like no light can escape. Which, so like, yeah.
Oh, wait, is this going to be public?
All clients are important, Mike.
So, black holes, because they are so dense, they create really big bumps in the trampoline of space-time. So if you're going to measure something that's going to be a fluctuation in that, then you want something really heavy. So a black hole is a good way to do that. What's even better is if you have two of them and they're going to crash into each other, which is actually kind of cool. But no.
Oh, it's really cool.
It's really cool. It's not necessarily good for them. So these are just some pictures that kind of demonstrate that. That one's really complicated but pretty, so I put it there. So when you come to like space-time as your rubber sheet, that's kind of like what you can picture with this picture, which is a little easier to understand, is that as they rotate around each other because they're really heavy, they're going to actually make space-time around it ripple. And as it ripples, that's something that we can potentially detect. Now, it takes incredibly sensitive equipment to do that because, well, they look big in that picture. The fluctuations are actually very small. And then this is kind of a cool picture that I saw from somebody did a little video on it, which I have a link to on the next slide, but like showing you what it would kind of look like. I mean, this is like using a picture of, I think it's our night sky, and that's kind of what it would look like if you had a black hole doing that here.
Looks like a fetus.
Yeah, there's a bunch of different pictures. I wouldn't put it that way, but you know, okay. So this one has a link, which I'm not even going to try with this thing to make it work, but it just shows kind of that image of them colliding. And so so this is just showing the waves and Earth detecting them. And so I'm not going to describe the apparatus in which we used because that would take another like 5 minutes or so to do it. But recently they had a measurement, it's taken a really long time for us to have equipment sensitive enough to measure these like waves, to read them. And so like recently they just found them, and they're a huge deal because of a bunch of I have a couple of scary looking equations here just because they're fun. Like I think they're scary because like one of those represents like 16 different formulas, and that's scary. Anyway, so one of the things we're trying to do is confirm Einstein's theory of general relativity, which we've had a few things over time that have confirmed it, just because it's so I guess it's more in depth than things like you learned in high school with like Newton of how to describe the universe. So it's confirming another prediction that his equations had, which is neat. And then also because we use waves to detect things and whatnot, we can be able to potentially look at things and detect things in the universe a different way, or just have a different way of looking at things now. So it's just interesting for the things that we can potentially do with it in terms of science. So that's why it made it as a big deal, because we've been trying to find them for decades and finally succeeded. And so now that we know how to detect them, it makes it easier to see them elsewhere. And that's really all I have.
I got a simple question. What's a space-time?
It's a rubber sheet.
Yeah, aren't you paying attention? It's a rubber sheet.
Oh,
I wanted to capture the quote about the trampoline.
so
It's space's trampoline.
so
It
if
is
it's
a
a black
It was a
hole,
good quote.
Well, if you can imagine a heavier item or thing or person on a trampoline will make it go down really far, indent further, make a bigger impression on it than
Sometimes
a
I
lighter
touch the
object.
ground.
But
So-
how do we know the space-time exists?
Oh god, I think we're
You don't want to get into that.
So are there any other questions? Oh, Chris, you
How
have
do
a
we know the
question.
universe?
Can a black hole be a
Exactly.
wormhole then, like in Star Trek?
Well, there are theories with that. I can't answer that definitively because, okay, Chris, what else?
Does the multiverse exist then, like in Marvel?
Possibly.
Boom!
But maybe not exactly like Marvel,
What's
but
the-
it's possible.
What's on the other side of black holes then?
That's so cool.
We don't know.
Like, if
White
it's-
spot.
Do you think there is something on the other side?
Yes, white spot. We don't know, because no information can escape a black hole. So if we put anything in to try to figure out where it went, we'd never hear from it again anyway. Yes.
Right. So my question is, now that we've discovered, I need your prediction for how long till we have anti-grav.
Wow. I'm gonna defer to.
No. You're the presenter. Come on,
I
prediction.
have, okay, so I don't know, because anti-gravity is there's so much we don't understand about gravity to be able to make that happen soon. Like, there are 4 forces that we know of, and gravity is kind of the strange one.
Is
that
one of
doesn't-
them the force?
Yes, of course it is.
They explained that.
But
I was waiting for the super sun.
yeah, but gravity kind of doesn't fit in as nicely with the others. It doesn't play well with the others, so it's really hard to predict something like that. It's possible, but I don't know when.
All
We
right,
can get
Ram's
one.
got one last question, then we're done.
So the gravitation waves, do we anticipate any earthquake as a result of
No,
such?
no.
Like if
They
you look
don't.
After a while or something.
They're so small. Like we're detecting like a tiny ripple in like a laser beam that would I don't know, be the size of like an atom. You're not talking about something very big.
Gravity is
So-
considered one of the weak forces.
Yeah, it's, believe it or not, like you can jump out a window and it would seem pretty strong, but it's actually pretty weak. Well, I mean, one thing I like to use as an example for that is like
Don't
if you,
try that. by the way.
Don't use
yeah,
that
don't
as
do
an
that.
example.
If you drop a magnet on the floor,
Not from
like,
our window, anyway.
if you dropped a magnet on
What
the
if you do?
floor, you have the entire Earth acting against you when you try to lift it up. Like, so you're fighting so gravity makes it fall to the ground, but you can just use another magnet to pick it up like nothing. So you can see that's how weak gravity is.
That's a
So-
good analogy. I've never heard that one before. Good job.
I used to actually have magnets that I use in demos at labs to do that, and it was cool. Except one, the magnet didn't work, and it
All right, one more clap.
Thank you.